Buenos dias, amigos tensores. Good morning, tensor friends. Uh, I have a question here. I'm going to try to answer. Okay. I think I'm going to give you more than you asked, but this stuff can be confusing. And I'm calling it Tensors for Beginnors, index notation. Okay. Let's get rocking. Let's go all the way back to a definition. A tensor is a geometric object that is invariant, does not change, under coordinate transform. So, as an example, a car traveling at 100 kilometers per hour toward the northeast is a vector, a tensor rank 1. So it has a direction and it has a magnitude. Now, this car doesn't care what coordinate system you use. It doesn't even know there is a coordinate system. It's going 100 kilometers per hour towards the northeast. That's it. So that's a tensor. Okay. It is invariant no matter what you want to do to it. All right. Just some basics. A scalar, like the number 4, it's a tensor rank 0. A vector, which we write sometimes like this, is a tensor rank 1. Then anything larger than that, we just call a tensor. Here's an example of a tensor with 2 indexes. So this is rank 2 the tensor, okay? So we got the basics. Now, when you first saw a vector written as a linear combination of its components and basis vectors. I'm not sure where that happens. I'm going to guess general physics high school. I'm guessing. Okay. They would have written it like this, your instructor. So you got a vector, you got two components. So we're in two dimensions. And they would have used I hat, J hat, or X hat, Y hat. These are the same things. Okay. So this is a linear combination of the vector with its components and basis vectors. And it would have been drawn like this. So you would have written down your basis of vectors, right? So the I hat goes in the X direction, the J hat goes in the Y direction. You want to count it over 1, 2, 3 in the I direction, 1, 2, 3, 4 in the J direction. You put your point there. Then you start from the origin, you draw your arrow. So this would have been your vector. Okay? Now, one of the nice things about this is that as you continue through school, things get more and more generalized, right? So later you may have generalized that vector we just looked at to look like this. So they would have said it has an X component and a Y component. It has an X component and a Y component times those basis of vectors. And even in my books, one of my favorite books is The Student's Guide to Vectors and Tensors. It starts just like this. Now, in my humble opinion, this is where the confusion it starts. If we had written this from day one like this, a component with an upper index and a basis vector with a lower index, this is a proper tensor, the syntax. Then as you move through school, you've seen this already, and I don't. The instructor doesn't have to explain what these are because you're probably not ready for that. But if you see it written like this instead of written like this, it makes just as much sense, right? What's the difference? So I think that's where we start out wrong. But what do I know? Okay, so later on, you could have seen that generalized like this, where we just said VI, EI, and we sum that over how many dimensions we have. So this could be 2 terms or 3 terms or whatever, how many you want. Then later on in school, now you're going way up, you would have seen it generalized like this, where the I is called the dummy index or the summation index. So when you see the same letter in the upper and lower position, this is called a summation index. And you know how many dimensions you're working in, so this would be 2 or 3 or 4 or whatever you're doing. Okay? Now, when you see an index in the upper position like this, just think changes against, contravariant. When you see an index in the lower position like this, think changes with, covariant. So you got two words here, contravariant and covariant, okay? So let's look at that vector we were looking at a while ago, the 3i plus 4j. All right, let's plot it again. And this time we're going to show its the components. So it has a Vx component like this. It has a Vy component, right? Vy component. Now, what's really nice about this, and the reason everyone loves Cartesian coordinates, is because these form beautiful right triangles. Do you see that? It's a right triangle. So this leg of that triangle, because there's a 90 degrees right there, this leg of this triangle squared plus this leg of that triangle squared is equal to this hypotenuse squared. Remember that? The Pythagorean theorem? So what is the length then of this vector? Well, it's the hypotenuse squared. All right, we take the square root of it and we get 5. So the length of this vector is 5 units, whatever they are. Units of length, okay? Now, this works because these basis vectors in the Cartesian, the coordinate, are called orthonormal. Ortho means they're 90 degrees apart, and normal means their unit length 1. So these basis vectors are 90 degrees apart, and you see they're 1 unit long, okay? That's why this simple equation works. Now, if you actually write it out the way you should, is you would say, here's my components, 3, 4. Here's my basis vectors, Ex, Ey. Now I want to multiply this times itself, which is written as the magnitude of V, is written like this. And one of the multiplications you can do in vectors is the dot product. So you're going to multiply this by itself. So here's the vector, dot, here's the vector again. So we FOIL this, right? So we go, the first 3 times 3 is 9, Ex dot Ex. Outer, 3 times 4 is 12, Ex dot Ey. 4 times 3 is 12, Ey dot Ex. Plus 4 times 4 is 16, Ey dot Ey. Okay, excuse me. The definition of the product is vector A dotted with vector V is equal to the magnitude of A times the magnitude of B times the cosine of the angle between these two vectors. All right, so let's look at these basis vector dot products. In an orthonormal, the system Ex dot Ex, we know they're 1 because we said they were. What's the angle between them? Well, they're on top of each other, so it's 0. So the cosine of 0 is 1. So it's 1 times 1 times 1. Now, what's Ex dot Ey? It's the same thing, 1 times 1. What's the angle between them? Well, they're orthogonal at 90 degrees. What's cosine of 90? 0. All right? So if we rewrite that equation up here, this is 0 and that's 0. So it drops out. And we're left with this, and we get V dot V equals 25. So the magnitude of V is 5. Excuse me. So that's why the Pythagorean theorem works in orthonormal basis vectors, because of what they are, okay? Now, what if the basis vectors were ortho, so they're 90 degrees apart, but not normal? What if they're 2 units long, right? Well, we go back to our equation. Now I'm just going to call them something different, EA and EB. Here's our 2 components that we had, right? So EA and EB are 2 units long. So we do the FOIL thing again. But we don't have to worry about these guys, right? EA dot EB, EB dot E. These are still 0 because they're orthogonal. We don't have to worry about them. But what's EA dot EA? Well, this time their magnitude is 2. So we've got 2 times the cosine angle between them, which is 1, is equal to 4. So these guys are 4, and this guy is 4. So we work that math out, and we get the square root of 100. Well, that's not 5. So what went wrong here? Let's look at it. All right, let's go back to our picture. What I did was I doubled the length of these basis vectors. So this one became 2 and this one became 2. So if I want this vector again, I only need 1.5 of these, right? 1.5. And here I need 2. So I have to rewrite my equation like this. This X component is 1.5 and this Y component is 2 because these are twice as big. Now when you crunch that math, you get 5. So what's that saying, right? When the basis vectors double, the vector components reduced by 1/2. This is contravariant component. This is a contravariant component. So that's what that means to have the index in the upper position. It means it changes against. So I changed, these went one way and this went the other way. Okay? That's really the point. So that's why this, written like this, VI, EI, both in the lower position, it's not a tensor equation. It's not invariant. Because you're going to say they both change the same way. When this doubles, this is going to double. Well, you can't do that. It's not invariant. So if you wanted a covariant vector component like this, right, then the basis vector must be in the contravariant, as in this. So this is a modern terminology where you have a contravariant component and a covariant basis vector, and these are called covectors. And when you see it in the contravariant component and the covariant basis vector, this is a vector. So we have two types of these things, and they do different things, okay? So that was just an introduction to why we do this like this, because it makes a tensor equation. Now let's look at the point of this was the free indices and summation indices, okay? When you see an equation like this and you see two indexes that are different, so you got I and J on this side of the equation, there's nothing else over here, you immediately know these are free. I and J are called free indexes. And whatever happens on this side, you can't change that. You have to keep using them in the I in the lower position and the J in the upper position. All right. So, and now if you see them like we've been doing, where you got the same index, upper and lower, and they're the same, then it's a summation index. All right. So these are two different things. This is a free index. This is a summation index. Now let's put that together. Okay. The covariant derivative, it doesn't matter if you know what a covariant derivative is. That's not the point. The point is it is defined as this operator acting on this vector component. So it's saying I'm taking the covariant derivative of the jth component with respect to the ith, the coordinate. So I got two free indexes, I and J. Now over on this side, I have all these terms, but I can't change this. So I had to put the J in the upper position and the I in the lower position. Now this looks like it's in the upper position, but it's not. If it's in the denominator, it's in the lower position. Now I have this thing here, the gamma, the factor, times this vector component. So I have to use J and I the same way, J and I. Right? So that leaves nothing here and nothing here. And we know this is more than one term. So this is where we put our summation index. Right? So you see these are the same and these are not free. Does that make sense? All right, so let's say we have working in 3 dimensions. And we write the dimensions as x1, x2, x3. These are not exponents, they're indexes. All right? So we have this vector VIEI. So this is a summation index. So we go 1, 2, 3, right? So this means this. Now, what if we take the covariant derivative of one of these components? Well, I'm going to choose the vector component V2, and I want to take the covariant derivative of that with respect to x1. So we write down our normal partial derivative, just like this. Now we got all these gamma factors, right? And we're going to have 3 of them because there's 3 dimensions. So we got our free indexes are 2 and 1. We got 2 and 1 here. Now look at this, Ji. So everywhere we see a J and an I, we have to put a 2 and a 1. 2, 1, 2, 1, 2, 1. And we know this is a summation index, K is. And we've got the 3 dimensions, so this goes 1, 2, 3, right? So this means this. All right. Okay. Now what if we had a mixed index to tensor like this one? So it has a contravariant component and a covariant component. So let's do the same thing. Let's take the covariant derivative of this because it does demonstrate a lot of things. Okay. So here's our generalized equation that we have, but this time we have a two index to tensor. Okay. So what are our three free indexes? I, J, K. On this side of the equation, they're the only things over here and they're all different. Okay. So the rules are for every index, you have one of these terms. So you see, I got one index, I had one term. It's in the contravariant position, so it's a positive. When it's in the covariant position, it's a negative. It doesn't matter why at this point. It just is. Okay. Now think about this. So I got these three, the free indexes. So I put them in just like this. So this is the normal partial derivative of that tensor with respect to that coordinate, I, right? So we write down our terms. Now, how are we going to put all these things around? Well, let's say this gamma factor here, I've got three free indexes. Why don't I just go IJK? Well, what are you going to put over here? Do you understand? So I've got I and J. I can put them here and the K up there. That leaves this with nothing there. I make it a summation index. Now for the next term, I just do the opposite, right? So I make the summation index went from upper to lower. I make it go from lower to upper. That leaves only I and J and K open, which I need I, J, and K to be the free indexes. So that's the way I learned this, uh, was to keep writing these equations out and just saying, well, if I did this, what do I got? And eventually the pattern just sticks in your head and it won't be that difficult. Okay, I really hope that helps. If it doesn't, let me know.